we have next Professor Vishkin.
Okay, so I'm going to talk about two complementary agendas. The first one, I hope, will have a broad reach out because almost everything you do in computer science, engineering, data science falls under trying to do something within computer-aided reasoning. The second thread will be looking for a many-core computing killer app. And some of you may wonder or may think about the second topic as a bit more esoteric. So I would like actually to suggest to you as fresh graduate students whose biggest decision will be to choose a research topic and a field to work on, to actually test your ability to identify where cool and high impact problems arise. So what is a good way to do it in a risk-free fashion is to ask, suppose I was, say, 15 years older, and I came here not in 2019, 2004 to 2009, something in this range. What would I have bet on? So it turns out that when you asked many students during this time, those interested in AI and the type of problem I mentioned before, what would they have told you? And trust me that that's what they say. Computers are already strong enough. We want to work on applications. But if you go back and look at probably the most important contribution since the year 2000 to deep learning, it is actually in the intersection between improving computing performance and connecting it, building the bridge to deep learning. And those of you who need a reminder, GPUs enable deep learning by enabling stochastic gradient descent, by enabling fast matrix multiplication, and this in turn became a killer application for GPUs. Okay? So if you felt that this is on the esoteric side, maybe you need to tune up your understanding, and actually it's very constructive to criticize yourself and ask, had I observed that this is going to be the next hot things? So now the way it happened was a form of a miracle, some serendipity involved in it, but what is important is to take into account that not only for deep learning, but also for boosted decision trees, performance and known packages, XGBoost, has been an enabler. So machine learning has been a beneficiary of improved performance. Parallel computing benefited from a killer application. So you see that there is this strong interaction, and I actually believe that some of the high impact work which is waiting to happen is going to fall in this intersection. Both of them actually need more applications. Now, if you look at this slide, I looked at this slide after putting it together. I said, I don't want this story to be told to me. It's too technical. So let me tell you an alternative story. So I'm going to tell you about a really key challenge in biomed. So imagine that you have a friend who tends to get drunk in the evening. The guy still is able to think coherently, but his hand started trembling. So, and this guy is also an avid texter. Okay, so you know that you're going to get, after he drinks a couple of glasses, you're going to get some text from the guy. His hands are trembling, so what will happen with the text? Every word will be garbed up, and since the guy also has some automatic text correction, it's going to be garbled out furthest. Now, he sends you a message, and you would like to understand what the guy is saying. So how will you start making sense of the text that you get? One way is to take each word and try to understand it separately. What is the other way? To try to look at the whole sentence and see whether it makes sense. Turns out that the way that many people who do genomic sequencing for historical reasons and some other good reasons have actually worked exactly in the way that we find objectionable, meaning they would parse every word separately, figure out local mutations, and then try to make sense of it. Turns out that there is an interesting collaboration I have with the National Cancer Institute where you can actually observe some structure or get from the clinicians some structure on how an evolutionary tree that you would like to get out of mutations, with some constraints that it must satisfy. And if you put these constraints into your global analysis, things start making sense. And you can start telling where you have mutations and where you do not have, and come up with the correct analysis. Now, how do you solve such problems? So you can, it turns out that there is a nice, very nice recent reduction by a colleague there who happened to have gotten his PhD with me in '97 from computer science here, a fellow called Zainal, who just moved to NCI as a senior researcher. And he reduces it to SAT solvers or more satisfiability solvers, or more precisely, to max SAT. So now it turns out that in order to get the performance boost you will need parallel computing, and this is a bit challenging because people don't really know how to do it well for reasons that I'm going to mention next. So what's the state of the art on many-core computing? Till 2004, the clock speed advanced at a very high pace. This was called historically sort of Moore's law, but it stopped advancing. The clock speed of high-end processors today is the same as 2004. No more than 4 gigahertz, give or take. But recently, many of you know that the standard textbook we use for computer architecture classes, say to senior level students or to graduate students, is the well-known Hennessy-Patterson book that saw its 6th edition in 2017. And look at their admission. They say it seems unlikely that some form of simple multi-core scaling will provide a cost-effective path to growing performance. So they say vendors and we computer architects don't know how to do it. So what did I want to tell you about the work we have been doing here at the University of Maryland? I was originally a theorist on one of the founders of the theory of parallel algorithms in the 80s and early 90s. But then I said, I'm not going to trust architects because parallel computing was on the horizon. I'm going to come up with my own architecture. And my own architecture has been very different in the approach. The way that architects tend to work, also because they are funded by industry and vendors are tend to be quite conservative, they actually apply an approach which I would call build first, figure out how to program later. The approach that we have developed here had first a theory of algorithms that became the main theory of parallel algorithms, and then the whole idea of the architecture was to support this theory effectively. So it was designed, it integrated the theory, it was designed for fine-grained irregular problems, thoroughly prototyped in the form of hardware, software, parallel algorithms, and so on. Now, modern SAT solvers are great, but for SAT parallelism, it is too fine-grained with too irregular flow, and it can be limited, the parallelism, too limited for current GPUs and multi-cores to efficiently support. I believe that on my approach, which is called XMT, you can break this wall. Now, I stole shamelessly a prior slide from one of the talks in the morning because the flow of build first and figure out how to program later is quite clear here, right, when you see the distance of the toilet paper from the seat. So, conclusion. The research question is how to develop a killer application for a many-core architecture, and in particular in the computer-aided reasoning space. I'm trying to be not too partial here. It's fine if you do it on an off-the-shelf processor. It's even better if you will. But the research stage project that we have done here, and you are welcome to look it up, I believe has a bigger potential. It's much more challenging than meets the eye. And the question is, can parallel SAT, or more generally computer-aided reasoning, rise to a killer app? and other applications. What can you do next? So parallel algorithms is a very different way of thinking, and it's really an alien culture. It's a first principle type of thing. This is one of the things that you need to get in a class, because to get the next item in the sequence of courses, if you know it, and you are a graduate student, and if you came here, you're probably a very strong graduate student, you will be able to pick it on your own. But it will be very difficult to learn first principles by yourself. This is a course that I'll be teaching in spring 2020. It will help you gain better insight into deep learning and GPUs. And you are welcome to come by, talk to me, and of course, take the course. Okay.